Good morning, everybody. This is Mr. Ainsworth, and we're going to get into a review on exponential functions, graphing them. And I'm going to throw in some linear stuff too and do some cool things with the calculator. So have your T84 graphing calculator out or some kind of graphing calculator that you have and work with me here. We're going to do most of it by hand, but we're going to kick in this when we need to, okay? So let's take a look at our first problem here. We got an exponential function base 2 given here. We want to graph y equals 2 to the x power minus 1. That's base 2. And we have a linear function y equals 2/3 x plus 1. That's in slope-intercept form. We're going to graph them on the same coordinate plane. And we're going to find the intersection of the two functions. Okay, we're going to find the intersection of the two functions. So what we're going to do is we're going to graph the exponential first by hand, and then we're going to verify with the calculator here and make sure it's all looking good and correct. Okay, so we're going to start off with a domain of, let's say, -3. Start there. So 2 to the -3 power minus 1. We always rewrite this, handle the exponents first. This is 1 divided by 2 cubed minus 1. That's 1/8 minus 1, or -7/8. Okay, so we always do by hand, and then what we'll do is we will, like I said, verify it with the graphing calculator. So on the next one, we have 2 to the -2 power minus 1. That's 1 divided by 2 squared minus 1, or 1/4 minus 1. And since small minus big is negative, this is going to be -3/4, because if you take out 1 from 4, then 3 out of 4 remain. When x is -1, we have 2 to the -1 minus 1, which is 1 divided by 2 to the first power, or just 1/2. Minus 1 gives you -1/2. When x is 0, you have 2 to the 0 power minus 1. Any non-zero number raised to the 0 power is 1. So this becomes 1. Minus 1 gives you 0. So it passes through the origin. So we have our x and y intercept here. This is not only a y-intercept, but it's an x-intercept too, because guess what? It's on both axes, right? And then we have 1, so 2 to the first power minus 1 is 1. 2 minus 1 is obviously 1. When x is 2, we have 2 squared minus 1, or 4 minus 1, or 3. Notice how I'm stepping things out here, as I always do for you guys. We have 2 cubed minus 1 here, and we know our 2 cubed very well, base 2. Powers of 2. Powers, okay, of 2 are 2, 4, 8, 16, 32, 64. You guys know the drill. Okay, so 2 cubed is 8, so 8 minus 1 is 7. And then we have 4, so 2 to the 4th power minus 1 is 16 minus 1, or 15. So with this many points, we can graph this in this exponential function and get an idea of what it looks like. Okay, and this is a growth function. Okay, base 2 right here is growth function, so it should go to the upper right. It should go, okay, way up like that. All of these values, all of these range values are greater than -1. And this right here will give me an idea. I know I'm expecting a horizontal asymptote at -1, so, and that makes sense because all of these values, the range values, the range, or y, okay, is greater than -1. All of these values are greater than -1. Okay, -7/8 is close to -1, but it'll never be equal to -1. So that you'll see that in the graph. Okay, so we're going to go left 3, down almost 1. So 1, 2, 3, down almost 1. -7/8 is almost -1. Okay, left 2, down 3/4. Left 2, down 3/4. Right about there. And then left 1, down 1/2. And then at the origin, like I said, then 1, 1. And then 2, 3. 3, 7. And then 4, 15, which is right 4 up all the way up here. Okay, so we have a horizontal asymptote right here. Actually, I'm going to make it look real good, okay? We have a horizontal asymptote at -1. I'm going to label that HA, okay? Y equals -1. That's why the graph lies above it, okay? And you'll see this when I graph it on the T84. Okay, so there's y equals 2 to the x minus 1 in blue. You'll notice how it's asymptotic, and it approaches the horizontal line, but it'll never reach it, okay? Asymptotes, or the functions, approach the asymptote but never never reach it. And so you'll get infinitely close, but never reach it there. Okay, and now let's go ahead and graph the linear function right here. So linear function, so y equals, let me put that in black. So y equals 2/3 x plus 1. Well, y equals m times x plus b. So right here, I see a slope of 2/3. So up to right 1 from the y-intercept of 1. So I'm going to do this in green just for funsies here. So I'm going to graph this at 1, starting at 1, excuse me. So that's your y-intercept at 0, 1 on the linear function, that is. All right, and then I'm going to go up to right here, right 3. That's a slope. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. And so what we can do is we can graph this function here, this linear function. That's pretty accurate right there. There we go. So it intersects the function at 2 different points. Okay, right about here. I see an intersection point there, and I also see it right about here. I see 2 intersection points. Okay, so right here, we can only approximate it. We'll get the actual value. So it kind of looks close to maybe 1.5, 2. So I'm going to write down 1.5, 1.5, 2. That's one of them. And then down here, I don't know, it looks like -3, almost right there at -7/8. So -3, -7/8, or maybe, I don't know, 0.8, 0.9, something like that. Okay, I'll use decimals. Don't really know. That's why we're going to use a decimal. I mean the calculator, excuse me. And I'll show you how to intersect that. Okay, so speaking of calculators here, let's take out your T84. Let's enter the functions in, and let's take a look at the graph. Okay, so the very first step, you hit the y equals button. That's called the equation editor. And you're able to enter in 9 different functions here. So we're going to enter in the exponential function first. We go 2 to the power of x. There's my exponent button. I got to go right arrow and get out of the exponent, and then I'm going to subtract 1. Okay, look at that, y equals 2 to the power of x minus 1. Then I just go down arrow to y2. So you guys, this is y1, function 1. This is y2, call it function 2. So y2 is going to be the linear one, and we're going to type in 2/3, so 2 divided by 3. Okay, and then times x, and then plus 1. So we go plus 1, and then go zoom. Don't hit graph yet, hit zoom, and then select number 6 for standard. Watch what happens. y1 is always plotted first, is the exponential function. And the next one here, we should see the linear function in red. Right here, that's y2. And the reason why it's in red is because, guess what? If you look right here, y2 is in red, and the first one, y1, is in blue. It's color-coded. It's kind of nice. So let's go back to the graph. Now we want to find the intersection point. So let's find the first one here. I'm going to hit, first of all, I'm going to go to trace mode, and I'm on y1 right now. So I'm going to go to the left to get to the intersection point. Kind of hard to see because we're zoomed out. So you know what? As soon as I get close, I'm going to zoom in. So I'm going to select zoom. I'm going to go down arrow, and I'm going to hit the enter button twice. Okay, you got to hit it twice, and watch what happens. Okay, so now you'll see why the blue one is the exponential, and you got the linear one. And you could tell I was close, but I didn't really get there. I'm going to go to the right a little bit, get a little closer. So that's close. So x is about 2.7. So you can tell my estimate, -3, 0.8, was close, but it wasn't quite good enough because the real answers are about 2.7, 0.8. So it's close on the y value, but not on the x value. That's because I graphed it by hand, and I'm not perfect. Okay, but let's get a better estimate here. Watch this. When you calculate an intersection, you got to calculate it. And notice the above trace is the word calc, right? But it's in blue. So you got to go blue and then hit trace button, and you want to calculate number 5, which is intersect. So you hit number 5 for intersect, and it always asks you two questions. What's the first curve? And it's always y1, so select enter. And it asks you the second question, second curve. Well, it's y2, okay, the linear function. Select enter, and it says, hey, what's your guess? And I'm close to the guess. If you want to go closer, you can move the cursor if you want, and then hit enter. And then the calculator uses a special method, a mathematical method, to find the intersection here that is very, very accurate. So here it's about 2.78 comma 0.85. I'm going to write that down. So my first one here, so it's 2.78. Let's read the calculator again. 2.7819, so 2.78 is close enough. And then 0.85. So 0.85. That's my first intersection point. Okay, so I'm going to highlight that. Now my second one is this one right here, so I need to find that. So I'm going to go back to the graph, and I'm going to zoom out here so I can see it better. You got to hit the enter button twice. And then I'm going to go back into trace mode, and I'm going to go up to the other intersection point. But I got to let the calculator graph, and on my computer here it's pretty slow. On your calculator it shouldn't be as slow. Hit trace, go to the right. No. Okay, get close. All right, now you don't have to zoom in. This is good enough. I'm going to calculate it. So I go second calc. All right, the calculator is color coded. So if anything in blue, you got to hit the second button first. Okay, and then select number 5 for intersect, and then go enter, enter, because it always asks you what's the first curve and second curve. And since we only entered y1 and y2, it's going to be the those two functions. So you go enter, enter. I'm already close to my intersection, so I'm just going to hit the enter for the third time. So go enter, enter, enter. And then look at that. It's 1.62 roughly, comma 2.08. So 1.6, I was close. So instead of this, okay, I'm going to go 1.6. Let me read the calculator again. 1.62, comma 2.08. So 2.08. Okay, so I was really close. 1.6 is close to 1.5, and 2 is close to 2.08. I was really close. So this right here is my second intersection point. Second intersection point. Right here. And so I graphed both of them, did it first by hand, verified it with the calculator, and then I found my intersection point. The last thing I want you to learn how to do is enter in your horizontal asymptote. And that's going to be y3. Okay, y3. I want to show you how or why this is correct. Okay, so I'm going to hit y equals again. I'm going to go down to y3. I'm going to enter in y equals -1. Okay, -1. So right there. It should come out in black. You know what? I'm going to clear that. I don't want black. I want that purple one. Let's go down to y4. So let's enter in -1. Hit graph. And watch this. You'll see it right here come out. So you can see how the function in blue, the exponential, approaches that horizontal line at -1. All right, if that's not close enough, well, then zoom in. Just hit the enter button twice. So first graph's the exponential. No, it's going to take off upward there. And then it's going to graph the linear function, the second one, 2/3 x plus 1. And then it's going to graph this horizontal asymptote. And you can see it's right below that blue exponential because we said it approached it. Okay? And that's how you enter in a horizontal asymptote. You can verify everything you do with the TI-84. Pretty cool, huh? Okay. Well, that's the first one, so let's go ahead and tackle the second one. The same idea, all the same concepts here, but different exponential, base 1/3 or decay, and a different linear. So when we have a base 1/3 right here, this is a decay function, and decay functions go like this. Okay, they get smaller, they decrease in values over time, so expect that. So it goes down versus goes up. So here we go. Let's start off with a x equals -3. We always start off with a domain, right? and then we calculate what's called the range, the set of y values. Remember, domain is x and range is y values. So here we have 1/3, all right, to -3 minus 2. The negative reciprocates this, so it's actually 3 cubed, so you always reciprocate first and then evaluate. And then 3 cubed, well, powers of 3, so powers of 3, what do they look like? 3, 9, 27, 81, 243. You guys know this by heart, so evaluating these should be easy. So this is 27 minus 2, all right, 25. When x is -2, you get 1/3 to the -2 power minus 2, which is 3 squared minus 2, which is 9 minus 2, or 7. We can graph that one. So we're not going to graph the first point, but we're going to graph the second point. Okay, sorry about that, guys. Getting a little crazy right here. When x is -1, we have 1/3 to the -1 power minus 2, and that's 3 to the first power minus 2. 3 minus 2 is obviously 1. When x is 0, we have 1/3 to the 0 power minus 2. That's 1 minus 2, or -1. Remember, any fraction to a 0 power is 1. When x is 1, we get 1/3 minus 2, which is just -1 and 2/3. When x is 2, we have 1/3 squared minus 2. That's 1 over 3 squared, because 1 squared is 1. 3 squared is, well, it's 9. So this is really 1/9 minus 2, which is a negative number. It's -1 and 8/9. Because if you take out 1 from 9, 8 remain, guys. Think pizza. Okay. 3. So 1 cubed to the third, 1/3 to the third power minus 2 is 1/27. 1 over 3 cubed is 27. So 1/27 here minus 2 is -1 and 26/27. Okay, that's good enough. Okay, so now all of these right here, the range, all of these, see, this is not quite -2 here. So all of this range right here, all the range values are greater than -2, and I expect that because of this -2 here. I can see that whatever, if I subtract 5, I expect a horizontal asymptote at -5. If I subtract 2, I expect a horizontal asymptote at -2, and so on. Okay. So let's graph. Let's graph from here down. Okay, you can't plot the first one, but you can plot the second one. So let's go left 2, up 7. So left 2, up 7. Let's go left 1, up 1. Let's go down 1 right here, 0, -1. There's your y-intercept right here. And let's see here. Should have changed my graph earlier, but that's okay. 1, -1 and 2/3. I'm off the graph. I'm going to approximate. So right 1, down 1 and 2/3. So right 1, down 1, and about 2/3. It's right about here. Right 2, down, almost down 2. So right 2, almost down 2. So right about here. And then right 3, almost down 2. Right about here. So I have a horizontal asymptote at -2. So I'm going to approximate that, even though I'm off the grid here. Down 1, down 2. So there's my horizontal asymptote, y equals -2. Remember, the range is greater than -2, so it lies above it. So when I graph this, it's going to decrease because this is a decay function. Whenever the base, come on, Ainsworth. Whenever the base is a fraction less than 1, you have a decay function. And there we go. So this is y equals 1/3 x minus 2, 1/3 to the power of x minus 2. Now I got to graph my linear function, 1/4 x minus 1. So I'm going to do that in green again. So I start here. There's my intersection point right there at -1, and then I go up. On my slope, I go up 1, right 4. So let me bring this down so we can see it better. So we go up 1, 1, 2, 3, 4, up 1, right 4, and then draw your function right there. Okay, so this one's easy. I'm going to verify this with a calculator, but here the intersection point, which is what we want to find, is at 0, -1. I'll verify that with a calculator. Okay, so what we need to do is re-enter the functions in, because last time they were different, right? So we hit y equals, and here we go again. We're going to clear it out. I'm going to go down and clear it out, go down and clear it out again. Okay, so here we go. Let's graph the first one. So quantity 1 divided by 3, put in parentheses. Oops, take a look at that. I got to be in the equation editor here. So quantity 1 divided by 3, right parentheses, raise it to the x power, get out of the exponent, all right, subtract 2. Go down, let's enter the next function, 1 divided by 4, and then times x, and then minus 1. And then to see the horizontal asymptote at -2, I'm going to put that in purple. So I'm going to go down to y4 here. I'm going to enter in -2. Okay, so you can see that in purple the horizontal asymptote. So here we go, zoom 6. And here we go. It's going to graph the exponential in blue first. Here it comes right here, and there's your exponential. Notice that it's down 2 almost. Here comes my linear function y2. Notice the intersection point right there. And then notice here at down 2 units is your horizontal asymptote, like I said earlier. Okay, now we want to intersect this. So what we want to do is go second trace, select number 5, and hit the enter button 3 times. 1, 2, and then 3. And notice the intersection right here is 0, -1, which is what I said earlier. Okay, so you can verify everything on the graph, you guys. All right. Okay. Now we want to do something cool. We want to apply it to a real problem. So check this one out, number 3. So let's read the problem first and take a look at what's going on. We got Ty and Antonio now. Now, Ty and Antonio have 2 different savings plans and initial amounts of money. We're going to analyze each savings plan first and then write a mathematical model. Okay, so mathematical model. You guys, that's a function, okay? A function which describes each one of these. All right, for each function, and graph each function. So we want to graph each function on the same coordinate plane. All right, so first we got to come up with the mathematical model. All right, so Ty starts off with $20. So notice it starts off. That's A sub I. That's your initial amount. And if they saves 20% money, saves, that means gains, the money grows. Okay, we have a growth function now. All right, 20%. Now 20%, that means that R is equal to 20%, which is 0.2 or 0.20 if you like. Okay, so to every week, okay, this is weekly here, she saves 20% of the money saved, or she saves 20% more of the money saved. So my mathematical model looks like is a exponential here. It's A sub I times 1 plus R, because it's a growth function, to the t power, number of time periods. So you can call this A sub F, you can call that Y1, let's say. So Y1, I first function here, because we're going to put this on the calculator here in a little bit, is equal to, all right, $20 now. $20 times 1 plus, all right, 0.2, or you can say 1.2, right? Raised to the t power. On the calculator, t is going to be x, okay, to the x power, okay, where x is the number of time periods. So time periods. In this case, weeks, okay, number of weeks. So we're going to have to graph that one. And then let's take a look at Antonio's savings plan. It's different. Okay, he starts off with $40 and saves $4 every week. Okay, so this is not exponential. Okay, not exponential. Okay, it's linear. So think y equals m times x plus b. And remember, this right here, as we talked about before, is what's called your initial amount. Okay, so this right here, your initial amount in this case is going to be your y-intercept at 40. And if you're saving $4 every week, that's going to be your slope right here, m equals 4. So my model here for the second function looks like 4 times x, right, plus the initial amount of 40. Okay, the question is, at what point in time will they have the same amount of money? Well, that's why we need to plot them on the same graph and figure out where they intersect. All right, the same amount of money. We need to find the intersection point. So find intersection point to determine that. So let's figure out after how many weeks. X equals question mark, number of weeks that go by. So let's figure that out. So let's graph these guys, okay, and we're going to have to use a table of values and generate this one here. Now, since we're dealing with number of weeks, the domain starts at 0. Time starts at 0 here. X can't be negative because weeks can't be negative. So no need to graph this. Well, we could start at negative, but I tell you what, the domain here would only be positive. We only consider positive values, but what the heck? Let me write it here. So Ty's mathematical model, let's go up here, 20 times 1.2. So 20 times 1.2 to the x power. So x here, the domain. Okay, in a real case, x can't be negative because x is number of weeks. However, we could enter it in and just take a look at it, but we're going to only consider x being positive, greater than or equal to 0. All right, when we're all said and done. And so my function looks like 20 times 1.2 to the x power. Okay, now, since we're dealing with number of weeks, we're going to start at 0, and then 1, 2 weeks, 3 weeks, 4 weeks, 5 weeks, so we can take a look at this and take a look at what's going on. So for at 0 weeks, we have 20 times 1.2 to the 0 power, which is 20 times 1, all right? Anything to the 0 power is 1, so that's 20. So there's your y-intercept right there. And let's see here. Notice that I started greater than or equal to 0 because the number of weeks right here, well, it's got to be greater than or equal to 0. So the number of weeks, x, or the domain, has got to be greater than or equal to 0. So I'm going to start at 0. What the heck? If you started at negative 2 or 3, that's no big deal. So don't worry about that. If you did, well, we just look at the part of the graph that's to the right of 0. That's it. So don't worry about if you had a domain starting at, say, negative 3 or negative 4. It's no big deal. So here we have 20 times 1.2 to the first power. Let's work that out. So 20 times 1.2. Whoa, I didn't mean to do that. I got to get out of here. Go second, quit. Okay, second mode. Quit out, clear it out. Okay, there you go. This is called the home screen. So go second mode, which is quitting out of the graph and get into your home screen, where you can do some math. Okay, so 20 times 1.2. Okay, that's 24. And then 20 times 1.2 to the second power. Let's get a table of values going here. So 20 times 1.2 to the second power. Boom. 28.8. 28.8. And then we got 20 times 1.2 to the third power. So 20 times 1.2 to the third power. Generate some values. Ooh. Okay, let's try that again. So 20 times 1.2 raised to the third power. You got to enter in the right numbers here. 34.56. So 34.56. Here we have 20 times 1.2 to the fourth power. Whew. Okay, that's my Great Dane barking out there. So 20 times 1.2 to the fourth. There's other ways to get a table of values, by the way. I didn't hit the right buttons, guys. See, I missed some numbers here. Calculators are great. However, if you don't press the right buttons, they don't give you the right results. Okay, so it's only as smart as you are. So 41.47. I'll show you a faster way to get these values here after I do this, but this is the step-by-step approach. Okay, and I always do step-by-step approach first, and then I'll show you the quick way. So 20 times 1.2 to the fifth power. 49.76. 49.76. I could just, if I wanted to, I can just keep multiplying by 1.2. I mean, that's another fast way, times 1.2, times 1.2, because that's basically what's happening here. You just keep multiplying by the growth rate. All right, times 1.2. Okay, you could do that. There's also another way that you can do this, and I'll show it to you in a minute. So 20 times 1.2 to the 6th power. So watch this. I'm going to do it this way first. I'm going to take my previous answer times 1.2. So times 1.2, watch this. I get 59.72 roughly. Or I can take 20 times 1.2 and raise it to the 6th power, right? And it'll be the same. See? Okay, so 59.72. Okay, so I got some order pairs and I can graph these. So let's go back. Okay, so 0, 20. Okay, 0, 20 is right here. And 1, 24. So right 1 up 24, right about here. And then 2, 29 roughly. You just have to get close. So 2, 29. I can't be that accurate, so I'm just trying to get close. Right 3 up 35 roughly. So right 3 up 35, right about here. And then right 4 up 41, let's say. So right 4 up 41. That's close enough. And then right 5 up 50. Okay, right 6 up almost 60. Okay, so here's my function so far in blue. Okay, it's going to curve down here because it's a growth function. It's going to continue way up. So that's my function 20 times 1.2 to the x power. So y equals 20 times 1.2 to the x power. Now I have to graph Antonio's savings plan. So my slope is 4 and my y-intercept is 40. So I start at 40. Okay, so I'm going to go green now. So start at 40. And then, so y equals 4 times x plus 40. Now here, the slope is 4. And that's the same thing as, come on, it's the same thing as 4/1. So I can go up 4 right 1 if I want, which is right about here, and then do that. Or I can go up 8/2, or I can go up, if I multiply this by 10, so I can go up 40/10, right? If I multiply it by 10/10. So any way you want to do it. So from this point, if I go up 40, I get up to 80. Oh, that's off there. I better not do that. So I'll tell you what, I'll just go up 4 right 1. Up 4 right 1, up 1, 2, 3, 4 right 1. Up 1, 2, 3, 4 right 1. Okay, and you can see what's happening here. It's going to intersect up here. Okay, so it looks like my intersection point is right around here. So that's the time that their saving plans are equal. All right, the point at which the savings plans, okay, are equal. Okay, so what is that? Okay, so that's about 6, 60. So 6, 60. The question is that close? Put a question mark. So what we need to do is go ahead and graph these guys and compare. So how close am I? I don't know. So let's enter the functions in and do the same thing as what we did earlier. All right, let's learn from the previous problem. So let's go back up to y1 and enter my new function in. Okay, whoops. Okay, so 20 times 1.2 raised to the x power. No, I'm in the wrong mode. Got to hit y equals. So let me try that again. So 20 times 1.2 raised to the x power. Go down to y2, enter in 4x plus 40. And on this one here, this graph's got some pretty good sized numbers here. So I'm going to select, we'll try number 6 again, but I think that's not going to be good enough. I think we're going to have to adjust the window. Yes, we will, because I can't see the top here. I can only see close to the origin. So in this case right here, when this happens, the first thing I do before I adjust the window here, see it's graphing my linear function, I cannot see the intersection in quadrant 1. Okay, so what I'm going to do is I'm going to go zoom stat number 9. So everybody hit number 9, zoom 9. That didn't do it. Okay, so we're going to have to adjust the window. Okay, so let me talk about the window. So in order to see what we see on paper, like right here, I need to take a look at this number here. Now this is called Y max. Okay, and what we're going to need to do is adjust the window. Okay, I want to set Y max to 70. So Y max I'm going to put to 70. And the Y minimum, well, it's got to be above 0. So Y min, we're going to set equal to 0. X minimum, we're going to set to 0 too because it's greater than or equal to 0 on the domain. And X max, well, we don't have too big of X values, so I'm going to set it equal to, let's say, 15. Okay, this is 15 right here. We can probably deal with 10. Either 10 to 15 is okay. So X max, let's go X max here. So X max, set it to 15. That's this number here. Now, so where's the window setting so we can see this on the graphing calculator? So let's hit window. Oh, it's right there, right on the topic calculator. So we're going to set X minimum to 0. We're going to set X max to 15. 10 would probably be okay. We're going to set Y minimum to 0 because it's above the X axis. And we're going to set Y max to 70 so we can see everything. Okay, so now I'll hit graph. Boom. Let's see if we can see the intersection point here. Okay, so it's right there. Okay, so let's see here. Let's go trace. And I'm going to enter in 6 and hit equals. We're getting close, so go to the right. And notice it's 6.4 here. I said 6 comma 60. It's actually 6.5 comma 65, so it's close. But let's get even better. Okay, let's calculate it. Let's go second trace. Let's select number 5 for intersect. Select enter twice. And then one more time to guess, for the guess. And here we go at 6.57 comma 66.28 or 66.29. So 6.57, 6.57 comma 66.29. So 66.29. So this was close, but this was better. So my intersection point that I'm going to use is this right here. So at what point, the point at which the same planes are equal, guess what? X equals 6.7. So 6.57 weeks. Okay, after that, who has more money? Well, then the answer to that question is whoever belongs to this blue graph right here, because guess what? It's higher and gets steeper versus this line right here, this linear function here. So who has the exponential function? Okay, and guess what? Antonio was the linear one, so Ty was the exponential. So I'm going to write down Ty here. So this is Ty, and the black here, the linear, was Antonio. All right, so after 6.57 weeks, so after 6.57 weeks, all right, Ty will save more money. So Ty will save more money, okay? And that's what we want to answer, I think. So let's go back and read the question here. At what point in time will they have the same amount of money? We answer that. Let me get that value again. 6.57 weeks, 6.57 weeks. Make sure you say weeks. Who will have more money saved after that point on? Okay, I already explained that. Ty will. Okay, because her graph grows faster because 2 to the x power, excuse me, not 2 to the x power, because exponentials grow faster than linears, okay? Because exponential functions grow faster, okay, than linear functions. Sorry it's small, but there you go. All right. So you want to have an exponential situation when you save money as opposed to a linear function. So rather than putting a constant rate or a constant amount, because this is constant, okay, what you want to do is put more and more money in, and that's what happens when you take a percentage of something. As the money grows, the percentage of it ends up being more, okay, because it accumulates and grows faster. Okay, so rather than putting a constant amount in, you will put more and more and more in, and it becomes exponential. So remember that exponential functions grow faster than linear functions. So that's a big point of this lesson right here. Okay. All right. Now this is a video, right? And as I said in all my other ones here, if you need to listen to this again, rewind it. Okay. Listen to it as many times as it takes to understand it, so that you can be able to handle all of these on your own. All right, and that's all it takes is hard work, dedication, perseverance. All right, and the desire to do well. Okay, I explained the best way I can. This is Mr. Ainsworth, and I'll see you in my next lesson later on. Uh, make yourself proud and work hard. Bye bye.